$5.50 an hour, and that was greater than the minimum wage. I'm old. All right, ladies and gentlemen, we again are going to get into our last chapter today. We're going to split the notes up, so we're not going to do too many notes today. We're not going to do too many notes on Tuesday. Okay? So I think we're going to do about 6 short slides today. And we are getting into the periodic table and learn about the history of it in this first section. Then we're going to just start getting to know it. I know at one point, I think it was in your sixth grade, I think is when probably the last time we really covered the periodic table. If you plan on taking any chemistry the rest of your high school career, knowing the periodic table, the history behind it, what things called trends on there, and just knowing the layout and how to easily access information from there is going to give you a leg up for any future classes you're going to take. So let's look at the history. So the periodic table has actually only been around, a developed one, for about 150 years. I know it seems like a long time, but in the grand scheme of things, it's not that long. And so the 1700s, Lavoisier, again, this is really not the real development of what we know as the periodic table. This is the beginning of like kind of organizing information. Antoine Lavoisier compiled a list of all known elements at the time. And so at the time, they knew about 23 elements. Silver, gold, oxygen, and carbon were known, some very basic ones. And again, these have existed. These elements have existed since prehistoric times. I mean, they've been here quite a while. But if you look at what they called substances back in the 1700s, it's kind of funny. Like they had old English names, obviously. And so these simple substances like gases, they thought light was a gas, heat was a gas. And then they had what was called dephlogisticated air, as well as phlogisticated gas. And what it was like flogate or flogate. I think that's what it was. It was a substance that they thought was present in everything that was combustible, so part of fire. They thought it was its own entity. So the dephlogisticated air was air that did not have the flogate. Then you had the phlogisticated gas that contained the flogate, so the stuff that would burn. So it was interesting to always see how even the intelligent minds at the time still were uncertain, but they were trying to make sense of the world. In the 1800s, brought a large amount of information. And so once we started discovering more and more elements, we needed a way to organize the knowledge about these elements. So at the time in the 1800s, we were starting to get electricity. And so once we had electricity, we could use that to break down compounds into their individual components. For instance, water. We're able to break down water using electrolysis into hydrogen and oxygen gases, which those are the two components that make up water, if you didn't know that already. Then you have the spectrometer. We use this to identify elements. We also use the mass spectrometer to help identify isotopes, which are slight variations of the same element that have different masses. Then came the Industrial Revolution. So you are getting a history lesson today. So we were able to have this Industrial Revolution because of our expanded knowledge of the elements. These newly found chemicals, we were able to create soaps, dyes, fertilizers, things that really caused a boom in terms of production all across the board of industry. However, we were still learning about these chemicals and these processes. So we had a severe increase in pollution, to the extent where towns where they had these industries, after not a very long time, the entire town would be covered in soot and basically just all look coated in black. By 1870, we knew approximately 70 known elements compared to the 118 that we do know now. But a lot of the ones after the 70 elements that they knew about have been man-made. Most of them. There are still some that were naturally occurring. We just haven't found them yet. So, again, we continued our studies, continued researching, and we had, again, some more information that we were doing. An overwhelming amount of information, to be exact, on the properties of so many new elements and compounds was found in the 1800s. So again, we are still lacking that tool that allowed us to organize the facts associated with the elements. And so they came up with a plan. They came to an agreement that allowed for the scientists to accurately determine the atomic masses of the elements, and is all accepted, agreed upon. They said, okay, we're gonna start doing this. And so the mass values of the same element they found were slightly different for each scientist, just slightly. Which, you know, when you have slight differences, you end up having results that were hard to reproduce by another. And so if your scientific experiment cannot be reproduced in terms of the steps and the data that you obtain, it's hard to say that that particular procedure is validated. So then again, you have more questions arising. Okay, whose is the best way to determine this? But what they started to figure out was now the relationships between atomic mass and their elemental properties were able to be found. Along comes John Newland. We notice that when the elements were arranged by increasing atomic mass, their properties would repeat every 8th element. So first, the 8th elements would have similar properties. Now we start getting into the idea of a periodic relationship, hence the name periodic table. And so at the time, Newland said this is the law of octaves. Oct meaning 8. Again, every 8th element, you have a repeated chemical property. However, although this was a kind of a neat insight into how we could arrange them, still wasn't the right way to go about it. Okay, a lot of disapproval because the law did not work for all the known elements. And if it doesn't work for all, it cannot work at all. Again, their approach had to be scrapped. And they knew that there had to be some way to get this correct. That's when we have these individuals. Lothar Meyer, Dmitry Mendeleev, and I cannot remember his first name, Moseley. I think it's maybe Henry Moseley. I cannot remember his first name. But Lothar Meyer, Dmitry Mendeleev, they both demonstrated the connection between atomic mass and elemental properties. But Mendeleev is the one who really receives credit for this. The table that we use today, originated with Mendeleev, but there's a reason for that. He went ahead and arranged the elements in order of increasing atomic mass into columns with similar properties. He again, much like Newlands, noticed a periodic pattern in this type of elemental arrangements. But as he did so, based upon the patterns that he was seeing, he would purposely leave spaces in this table because he knew that some other undiscovered element had to go there. So of the known elements at the time that Mendeleev was doing this, there's about 62 known elements. I know it's 7, but when Mendeleev was doing this, it was about 62. And so what he would even do based upon his arrangement and the spaces he left, he would make predictions about those undiscovered elements. And when they finally discovered these elements, his predictions, going from color, properties, even atomic mass, as well as what chemical formulas it would create, were almost spot on to their actual scientifically accepted data. So, scandium, gallium, germanium, those are the ones that really stand out. Germanium especially. His predictions of its properties were the ones that were really, almost right on the money. And so his table became widely accepted. But the reason why his table became widely accepted is Meyer was pretty close to discovering the same thing too. He, Mendeleev that is, was obsessed with arranging these periodic tables. This one table wasn't the only one he created. He created table after table after table because he kept getting frustrated. He would spend countless evenings and hours getting this right. Then he started getting into this. He said he had a light bulb go off and say, there's got to be something else. That's when he started leaving spaces in there. But he was really the only one that got his name out there with this table and why he receives credit, because no one would publish his works. And he went ahead and said, all right, fine. He went and published his own textbook and therefore included his own table. And that table got distributed and accepted. In fact, he knew so much about the periodic table as well as the elements that there was a French scientist who said that they discovered a missing element and presented his data in a paper. Mendeleev read the paper and said, you're wrong. And without even seeing what this quote-unquote element that the French scientist found, he said, your data is incorrect. This is what it should be. And he proved him wrong. Dmitry Mendeleev proved him wrong without even having seen the object that was studied. So, what Moseley did, we haven't mentioned Moseley just yet. He went ahead and took the table and rearranged it by increasing atomic number, which is more so what we see today. Again, the atomic number is equal to the number of protons in each nuclei of the elements. And each element has a unique number of protons associated with it. Like every carbon will always have 6 protons. And so by rearranging the table, Moseley was able to show that several elements from Mendeleev's table would be placed in groups with differing properties. So we started to see a periodic pattern, more of a periodic pattern, with Moseley's arrangement. So then, once this started to work for all elements, it led to periodic law. Periodic law is defined as a periodic repetition of chemical and physical properties of the elements when they are arranged by increasing atomic number. So now that we've discussed a very brief history of the periodic table, the second half of these notes that we're going to get into on Tuesday, we're going to hop right into the setup and arrangements of the periodic table itself. Okay, we're going to stop there.